Given any open cover, and here is the symbol for open cover. Inside these parentheses are open intervals. Should I write that? Should I put it in? Yeah. Okay. Yeah, it's a review then. Okay. So inside we have open intervals. And then I will always do. So given any open cover, which is a set that contains open intervals, how many, whatever the number, for the for the closed and bounded interval. Is that, yep, that's what they say. I could put interval here, or I'll just put it here. Interval A comma B. All right, so this whole thing. Oh, well, I don't need to underline this. This is the statement of the theorem. I mean, just the first line of the statement of the theorem. When we have something called closed and bounded, closed means the endpoints are included. So endpoints are included. In here, we have infinitely many reals. Okay, and then there's one other thing. Bounded, we need to think about bounded. Does it mean this? And my answer today is no, it means this guy. So the bounded, of course, we're talking about. No, that's not right. Let's think about this. Shit, I was pretty sure about this. Upper bounds. Okay, so I'm gonna put these. Bounded just means upper bounds. It doesn't mean LUB. So yes, bounded means above and from below, which is actually technical terms, above and below. And so I'm gonna put dot I and then alpha dot I. And then we know we have to, in this theorem, we have to prove that this is LUB. Okay, so I think, yeah. Very good. We don't know, yeah, so we have to prove that. So this is correct. Bounded means it's on the, I mean, and this could be a bunch of upper bounds, right? Okay, so we got that. Next line is, okay, so I'm gonna draw the picture for just this line here. So for line 1, we have this picture. So we have O1, let's say O2, O3, and then bunch of ON. And this is the picture is for this one here. Okay, so this, I want to write, what do I want to write? I want to write open cover. Okay, all right. And then let's write the next slide. Have I missed anything here? No, I've got the closed and bounded interval. I could add something like this here, right? Just to follow up with that.
The bounds don't necessarily need to be in that cover, right?
No. So
Looks like a parent set.
Yeah, because the real parent is the big boss. Thank you for reminding me. The real numbers, the parent of this guy is, because A comma B is a subset of that guy. A comma B, the interval A comma B is subset of real numbers. Okay, number 2. And so I'm writing it down here because we're going to put the finite subcover. So if the word subcover should tell you it's an open cover with a finite number of open intervals. So just that word subcover is a smaller cover than this guy and a finite cover. Other by my blue one. Okay, I forgot. So this is what? This is what we assume. Given this, we assume it has an open cover. It is closed and bounded. Okay. And so this is, if we remember from last time, this is condition 1. And then this thing is our condition 2. And these we can assume true. And what we want to show is, and it's going to be here, is there exists, if this is the case, then there exists, I'm going to add that word here, just to kind of make it sound like a theorem, because the book doesn't have it like that. There exists a finite subcover. All right. Finite subcollection of sets in, that's what they're doing. I don't like that, but let's just do that. Finite collection of sets in, make sure that's what it says, in will include, it's such a terrible, all it should say is that there exists a subcover. Okay, so let's put that for our system. There will exist, if these two conditions are true, then there will exist a subcover that covers, fun. Yeah, if you say subcover that, yeah, but I could put finite subcover here. Oh, actually, it's right there, right? That covers the entire interval A comma B. All right, so let's do that. We're going to have the subcover here. And here is our O1. Let's say only 3 things are needed. That's how it does it. And so we're showing that our subcover is a set with 3 open intervals. And so this is finite. And this open cover here, because of M, implies possibly infinite. And then actually that's the whole deal. Okay, so now what is this? This is where we're supposed to get to in this. This is to show. We have to go from here and show that if you have this situation in blue, there will be a finite cover. All right, that's very clear, right? So theorem, THM, Heine, Borel. Is there 2 L's? Single L? I could be wrong. It is. Yeah, that was just me. Okay. So what's the first thing I'm going to put here, folks? Okay, very good. So it's going to be open cover. And you can of course, always look at your notes. The second thing I'm going to do is, what are we given? Yes, sir. And is there anything else? No. If you have those two things, there exists, these two things imply that there exists, and I'm just going to say subcover. Okay. One way to do the subcover would be, I don't know, there's no notation for subcover.
What's the
Oh, if there exists. You're not supposed to use it, but I like it. Like in an actual formal proof, you don't use that kind of notation.